Right now, somewhere in the United States, whether you're watching from a high-rise in New York City, a ranch in Texas, a suburb in California, or a quiet town in the Midwest, you are standing on the surface of a planet that was born in fire, not metaphorical fire. Real searing star-forged heat. 4.5 billion years ago. The ground beneath your feet did not exist. The iron in your blood did not exist. The silicon in your phone did not exist in any organized world. Everything that makes up Earth was once suspended in a vast, cold, invisible cloud of gas and dust drifting between the stars. And for all of human history, we have wondered, how did that chaos become this? How did a formless cloud turn into oceans, continents, mountains, and life? Today, for the first time in history, we are not just theorizing. Using the James Webb Space Telescope, humanity has peered deep into a stellar nursery and witnessed the earliest stages of a solar system coming to life around a young protostar known as HOPE 315. We are seeing in real time the kind of processes that built our own cosmic home. This isn't just another pretty space image. This is a time machine showing us our origin story. And if we understand what's happening there, we may finally unlock how Earth, and everything on it, came to be. If you're excited to explore the birth of worlds and uncover how planets form from nothing but dust and gravity, make sure to subscribe, hit that like button, and let me know in the comments where you're watching from. Are you tuning in from Florida's Space Coast, the Rocky Mountains, the deserts of Arizona? Drop your state and city below. I'd love to see how far this journey across the cosmos reaches. To understand what we're seeing with HOPE 315, we need to rewind billions of years and step back into one of the most dramatic environments in the universe, a stellar nursery. Across the Milky Way, vast molecular clouds, sometimes hundreds of light years across, drift silently in the darkness. These clouds are composed mostly of hydrogen gas, with traces of helium and tiny solid particles we simply call dust. Though the word dust sounds insignificant, these grains are the seeds of everything solid in the cosmos. They are made of elements forged in ancient stars: carbon, oxygen, silicon, magnesium, iron, created in nuclear furnaces and blasted into space by supernova explosions. Every atom heavier than hydrogen and helium has a stellar origin. When you hold a rock, you are holding the ashes of long-dead stars. Within these molecular clouds, gravity is always at work. Over time, slight variations in density, perhaps triggered by a nearby supernova shock wave or the spiral density waves of a galaxy, cause certain regions to collapse inward. As a cloud fragment contracts, gravity pulls more material toward the center. The region becomes denser and hotter. Eventually, the collapsing clump forms a protostar, a hot, glowing core not yet hot enough to sustain hydrogen fusion, but already radiating energy from gravitational compression. This is the earliest stage of star birth. As material continues to fall inward, it doesn't simply drop straight into the forming star. Because the original cloud had even a tiny amount of rotation, conservation of angular momentum causes the collapsing material to flatten into a spinning disk around the central protostar. This structure is called a protoplanetary disk. It is within this disk, this swirling pancake of gas and dust, that planets are born. Our own sun formed this way about 4.6 billion years ago. The disk that surrounded it contained all the raw ingredients of the solar system: hydrogen and helium gas, microscopic dust grains, and a mixture of volatile compounds like water, methane, and ammonia. For decades, scientists have built detailed models of how this disk evolved. They proposed that dust grains collided and stuck together, gradually forming larger and larger clumps. Millimeter-sized grains became pebbles. Pebbles became rocks. Rocks merged into kilometer-scale planetesimals. These planetesimals, through gravity, accreted more material and eventually became protoplanets. Over tens of millions of years, these protoplanets collided, merged, and sculpted the architecture of a planetary system. But until recently, much of this story was theoretical. We could observe mature stars with planets. We could observe young stars with disks. But the exact moment when hot minerals first condensed out of the gas, the time zero of rocky planet formation, remained hidden behind thick cocoons of dust. Traditional optical telescopes could not see through these veils. Even earlier infrared observatories lacked the sensitivity and resolution needed to dissect the innermost regions of embedded protostars. That changed with the launch of the James Webb Space Telescope in 2021. Positioned at the Sun-Earth L2 Lagrange point nearly 1 million miles from Earth, Webb is optimized for infrared astronomy. Infrared light can penetrate dense clouds of dust that block visible light. This makes Webb uniquely suited to study star-forming regions and the deeply embedded phases of stellar evolution. With its large segmented mirror and highly sensitive instruments, Webb can analyze the chemical fingerprints of materials within protoplanetary disks. When Webb turned its gaze toward HOP 315, located in the Orion Molecular Cloud Complex, astronomers saw something extraordinary. HOP 315 is a very young protostar, still wrapped in its natal envelope of gas and dust. This means we are observing it at a stage much earlier than typical protoplanetary disks studied before. Instead of a relatively clear disk around a visible star, we're looking into a system still in the process of forming its central star. And within that dense, warm environment, Webb detected signatures of hot mineral condensation, refractory materials crystallizing out of gas at extremely high temperatures. To understand why this matters, we need to dive into the physics of condensation sequences. In a protoplanetary disk, temperature decreases with distance from the central protostar. Close to the star, temperatures can exceed 500 degrees Celsius. At these temperatures, most solid materials cannot exist, they vaporize into gas. But as gas moves outward or as the disk cools, certain materials begin to condense into solid grains. The first solids to form are called refractory minerals, substances that can withstand very high temperatures. These include compounds rich in calcium and aluminum, such as calcium-aluminum-rich inclusions, often abbreviated as CAIs. In our own solar system, CAIs are found in primitive meteorites known as chondrites. Radiometric dating shows that these inclusions are among the oldest solid materials ever formed in the solar system. In fact, they mark the beginning of the solar system's solid history. For decades, scientists inferred that CAIs condense from hot gas near the young sun before being transported outward and incorporated into asteroids, but we had never directly observed this process occurring around another star. That's what makes HOP 315 so significant. Webb's spectroscopic data revealed emission features consistent with hot crystalline silicates and other refractory materials condensing in the inner disk. In other words, we are seeing the same kind of mineral formation that occurred in our solar system's infancy. This is not just a disk with gaps carved by forming planets. This is the chemical dawn of rocky worlds. The implications are profound. First, it confirms that the processes inferred from meteorites in our own solar system are not unique. The condensation sequence predicted by thermodynamic models appears to be a universal feature of star and planet formation. Second, it provides a direct observational anchor for the timeline of planet formation. Instead of relying solely on computer simulations and laboratory analysis of ancient rocks, we can now compare theory to real-time cosmic events. But how exactly do these tiny mineral grains become planets? The journey from microscopic dust to full-fledged world is one of the most fascinating transformations in astrophysics. Initially, dust grains in the disk are submicron in size, smaller than particles of smoke. Through electrostatic forces, these grains stick together upon collision. At low relative velocities, they form fluffy aggregates, somewhat like cosmic snowflakes. As they grow, their interactions change. Gas drag within the disk causes them to migrate inward, spiraling toward the star. This presents a problem known as the radial drift barrier. If particles grow too slowly, they fall into the star before becoming large enough to resist drag. To overcome this, researchers propose mechanisms like the streaming instability. In this scenario, concentrations of pebbles interact with the surrounding gas in a way that creates dense clumps. When these clumps become sufficiently massive, their own gravity causes them to collapse directly into kilometer-scale planetesimals. This gravitational instability can dramatically accelerate the formation process, bypassing the slow, incremental growth that would otherwise doom particles to destruction. Once planetesimals form, gravity takes over as the dominant force. Larger bodies attract more material, growing faster in a runaway process. Within a few 100,000 years, the disk may contain dozens or hundreds of protoplanets, embryonic worlds that will eventually collide and merge. In the inner regions of the disk, where temperatures are high and volatile compounds cannot condense, rocky terrestrial planets form. In the colder outer regions beyond the so-called snow line where water ice can exist, icy cores grow rapidly and may accrete thick envelopes of hydrogen and helium, becoming gas giants. The snow line plays a crucial role in shaping planetary architecture. In our solar system, it likely lay between the present orbits of Mars and Jupiter during the early stages. Beyond this line, the abundance of ice increased the solid mass available for core formation. enabling Jupiter and Saturn to grow massive enough to capture gas before the disk dissipated. Closer in, Earth and Mars remained relatively small and rocky. By observing systems like OPS 315 at such an early stage, we can begin to test whether similar snow lines and condensation fronts are present. Webb's infrared capabilities allow astronomers to map temperature gradients and chemical compositions within disks. This helps determine where different materials are stable and how they move over time. Another critical factor is time. Protoplanetary disks do not last forever. Observations suggest that most disks dissipate within 3 to 10 million years. This sets a deadline for gas giant formation. If a planetary core does not grow massive enough quickly enough, it will miss its chance to capture a thick gaseous envelope. The detection of hot mineral condensation in such a young system implies that the clock for planet formation starts ticking very early, perhaps earlier than some models predicted. The study of HAPS 315 also highlights the importance of multi-wavelength astronomy. While Webb provides unprecedented infrared sensitivity, other observatories contribute complementary data. The Atacama Large Millimeter Submillimeter Array, or Atacama Large Millimeter Submillimeter Array, located in Childs High Desert, observes the cold outer regions of disks at millimeter wavelengths. ALMA has imaged striking ringed structures in older protoplanetary disks, often interpreted as gaps carved by forming planets. By combining ALMA's view of mature disk structures with Webb's glimpse into deeply embedded protostars, astronomers can piece together a more complete timeline of planetary birth. For audiences across the United States, this discovery carries a deeper resonance. The Apollo missions brought back rocks from the Moon, allowing scientists to date the early solar system. Meteorites found in deserts and Antarctica preserve ancient inclusions older than Earth itself. American observatories and space agencies have played a central role in building the theoretical framework of planetary science. Now with Webb, a collaboration between NASA ESA and CSA, we are witnessing a confirmation of decades of research. The story of how planets form is no longer confined to textbooks and meteorite labs. It is unfolding before our eyes in Orion. Yet this is only the beginning. OPS 315 is one system among many. Each protostar may evolve differently depending on its mass, environment, and initial conditions. Some disks may fragment to form multiple stars. Others may produce tightly packed planetary systems unlike our own. By studying a statistical sample of young systems at various stages, astronomers aim to determine which features are universal and which are unique. In the coming years, further observations of HAPS 315 will track how its disk evolves. Will we see evidence of pebble growth, signs of disk winds removing gas, chemical gradients shifting as the protostar brightens? Each data point refines our understanding. Each spectrum is a clue in the puzzle of cosmic origins. For now, the key takeaway is this: we have crossed a threshold in planetary science. For the first time, we are not merely reconstructing the birth of our solar system from ancient remnants. We are watching another system begin the same journey. The condensation of hot minerals in HAPS 315 marks the dawn of rocky planet formation. Somewhere within that disk, microscopic grains are sticking together. Given enough time, they may form worlds. And perhaps billions of years from now, on one of those worlds, intelligent beings will look up at their sky and wonder how they came to be, just as we do today. Because seeing hot minerals condense around HAPS 315 is only the beginning. The real question is this: how does dust become a world? How does something smaller than a grain of sand transform into a planet the size of Earth, or a gas giant like Jupiter? The answer lies in a complex interplay of gravity, motion, heat, magnetism, chemistry, and time. And as we look deeper into the data from the James Webb Space Telescope, we are realizing that the early stages of this transformation may be far more dynamic and far faster than we once imagined. Picture the disk around a young star not as a quiet, orderly structure, but as a chaotic, turbulent environment. Gas swirls at thousands of miles per hour. Temperatures vary dramatically from the scorching inner regions to the icy outer fringes. Shockwaves ripple through the disk. Magnetic fields twist and snap. This is not a gentle nursery. It is an arena, and inside it, the smallest solid particles must survive long enough to grow. At the very start, the disk is dominated by gas, mostly hydrogen and helium. Mixed within it are microscopic dust grains inherited from the interstellar cloud. These grains are typically less than a micrometer in size. Their first step toward planethood is deceptively simple: they collide and stick. At such tiny scales, electrostatic forces are stronger than gravity. When two grains gently bump into each other, surface forces can cause them to adhere, forming aggregates. Laboratory experiments on Earth, including those conducted in microgravity environments, have demonstrated that dust particles can form porous, fluffy clusters. These structures resemble cosmic soot balls. In the disk around HOPS 315, as revealed by Webb's infrared spectroscopy, the detection of crystalline silicates suggests that grains are not only sticking together but also undergoing thermal processing, melting, recrystallizing, and chemically evolving. These processes change how grains interact. A crystalline grain behaves differently from an amorphous one. Its surface properties influence how effectively it bonds during collisions. As aggregates grow to millimeter and centimeter sizes, often called pebbles, a new force becomes important: aerodynamic drag. The gas in the disk does not orbit at exactly the same speed as solid particles. Because gas is partially supported by pressure, it moves slightly slower than the Keplerian orbital velocity. Solids, feeling less pressure support, try to orbit faster. This difference creates a headwind. Pebbles lose angular momentum and spiral inward toward the star. This is one of the great paradoxes of planet formation. The very process that allows solids to grow also threatens to destroy them. If pebbles drift inward too quickly, they will fall into the protostar before assembling into larger bodies. In our own solar system, something must have prevented this catastrophic loss. The presence of ancient meteorites containing early formed inclusions proves that solids survived long enough to become planetesimals. Observations of HOP 315 suggest that mineral condensation begins extremely early, meaning the clock starts ticking almost immediately. To solve this drift problem, scientists developed the concept of the streaming instability. Imagine a region in the disk where pebbles become slightly more concentrated than average. Because solids interact with gas, a higher concentration of pebbles can locally alter gas motion. This feedback effect reduces the relative speed between solids and gas, allowing even more pebbles to pile up. Over time, these concentrations grow denser and denser. When the density of solids exceeds a critical threshold, their self-gravity takes over. Instead of slow, incremental growth, the clump collapses directly into a kilometer-scale planetesimal. This process is astonishingly efficient. In simulations, streaming instability can produce hundreds of planetesimals in a relatively short period. Tens of thousands of years. That's a blink of an eye on cosmic timescales. If similar processes are occurring in HOPS 315's disk, then we may be observing the earliest chemical stage, just before gravitational collapse into solid bodies. Once planetesimals form, the growth regime changes entirely. Gravity becomes the dominant force. A 10-kilometer wide body exerts a measurable gravitational pull. When it passes near smaller objects, it can deflect their trajectories, increasing the likelihood of collision. This phase is known as runaway growth. Larger bodies grow faster because their gravity enhances their effective cross-section. Within a few 100,000 years, some planetesimals can grow into moon-sized protoplanets, but growth is not uniform. The distribution of material in the disk determines which regions form planets first and what kind of planets they become. Close to the star, temperatures are too high for volatile compounds like water to remain solid. Only refractory materials, metals and silicates, can survive. This leads to the formation of rocky planets. Farther out, beyond the snow line, water ice becomes stable. Ice dramatically increases the available solid mass. A core forming beyond this line can grow several times faster than one in the inner disk. In our solar system, the snow line likely lay between Mars and Jupiter during the early stages. This boundary may explain why Earth is rocky while Jupiter is gas-rich. The young Jupiter's core likely formed rapidly beyond the snow line, reaching a critical mass of around 10 Earth masses. Once it crossed this threshold, it began accreting gas in a runaway process, pulling in vast amounts of hydrogen and helium before the disk dissipated. The timing is crucial. Protoplanetary disks typically survive only a few million years before stellar radiation and winds disperse the gas. If a core fails to reach critical mass before that happens, it remains a rocky or icy planet rather than becoming a gas giant. Observations from facilities like the Atacama Large Millimetered Submillimeter Array have shown that disk lifetimes vary, but they are rarely longer than 10 million years. This narrow window shapes the diversity of planetary systems. As protoplanets grow, they begin to gravitationally interact with the disk itself. A sufficiently massive body can carve a gap in the surrounding material. Gas and dust are pushed away from its orbit, creating rings and voids. ALAMA images of older disks reveal spectacular concentric rings, many interpreted as signatures of forming planets. But in extremely young systems like HEP 315, the disk is still deeply embedded. We are seeing the stage before clear gaps appear, before the planets fully announce themselves. Collisions among protoplanets are inevitable. In the inner disk, dozens of Moon to Mars-sized bodies may coexist. Their gravitational interactions lead to chaotic orbits and eventual impacts. Earth itself likely formed through a series of such collisions. One of these impacts may have created the Moon when a Mars-sized body, often called Theia, collided with the proto-Earth. The debris from that impact coalesced into our natural satellite. These violent events are not rare anomalies, they are part of standard planetary assembly. Chemical differentiation also begins early. As protoplanets grow, radioactive isotopes like aluminum-26 generate internal heat. This heat can melt the interior, allowing heavy elements like iron to sink toward the center, forming a core. Lighter silicates rise to form a mantle and crust. Even small bodies can undergo partial melting. Meteorites found on Earth preserve evidence of these processes. Iron meteorites are fragments of differentiated cores from ancient planetesimals that were later shattered. The detection of refractory mineral condensation in HEP 315 connects directly to these meteorite records. Calcium-aluminum-rich inclusions found in meteorites are thought to have formed within the first 100,000 years of the solar system's history. If Webb is seeing similar materials around HEP 315, then we are witnessing an equivalent epoch. This is effectively the year zero of planet formation. Magnetic fields add another layer of complexity. Young stars are magnetically active. Their fields thread through the disk, driving turbulence and launching disk winds. These winds can remove angular momentum, allowing material to accrete onto the star. They can also strip away gas from the disk over time. Magnetorotational instability, an interaction between magnetic fields and differential rotation, may generate turbulence that influences how dust grains settle toward the midplane. Dust settling is crucial. For planetesimals to form efficiently, solids must concentrate in the midplane of the disk. If turbulence is too strong, particles remain stirred up and diffuse. If it is too weak, rapid settling may trigger gravitational collapse. The balance determines the efficiency and location of planet formation. Radiation from the protostellar also reshapes the disk's chemistry. Ultraviolet light can break apart molecules while X-rays can ionize gas. These processes influence which compounds form and where. Organic molecules, precursors to life, may arise in cold outer regions and later be delivered to forming rocky planets via comets and asteroids. The chemical inventory of a disk therefore sets the stage not only for planet formation but potentially for habitability. One of the most exciting aspects of studying systems like HEP 315 is the possibility of testing these theories observationally. Webb spectroscopic capabilities allow astronomers to detect specific molecular signatures, water vapor, carbon monoxide, methane silicates. By mapping their distribution, scientists can infer temperature structures, condensation fronts, and transport processes. For viewers across the United States, consider this. Every model described here was once built from equations on chalkboards, supercomputer simulations, and tiny grains extracted from meteorites in laboratories. Now, for the first time, we are comparing those predictions with direct observations of a newborn solar system. It is the scientific method unfolding on a cosmic scale. But perhaps the most profound realization is how universal this process appears to be. Thousands of exoplanets have been discovered orbiting other stars. Some are hot Jupiters hugging their stars. Others are super-Earths in tightly packed systems. The diversity is staggering, yet the underlying mechanism, the collapse of a molecular cloud, the formation of a disk, the condensation of solids, the growth of planetesimals appears to be a common pathway. HEP 315 is not special because it is unique. It is special because it is ordinary. It is likely following the same physical rules that governed the birth of our sun and planets. And that means our origin story is not rare. It is part of a vast cosmic pattern. As we continue observing this system, astronomers will look for signs of evolving disk structure. Are there asymmetries indicating clumping? Are there temperature shifts suggesting inward migration of material? Over time, we may detect hints of nascent protoplanets shaping their environment. In the end, planet formation is a story of transformation. It begins with microscopic dust forged in ancient stars. Through collision, instability, and gravity, that dust becomes rocks. Rocks become worlds. Worlds may become habitats. And in at least one case, our own, those worlds produce beings capable of asking how it all began.